Let's look at some of the optional arguments you can use with the testpropsC function. I've demonstrated the basic one sample test and the two different types of two sample tests. I'm going to put the documentation back on the screen. Okay, so I'm going to just run this code again, line 8, the one sample test, child manners against the hypothesized value of 0.5, and we get the table, multiple tables, and the plot. So some of the arguments are just to suppress some of the results if you don't want to see everything. So there is a ci table argument. By default, it's true, but if we don't want to get this last table, we could say ci table equals false, and we'll get the same tables again, descriptive statistics, the z-test, and then it'll just ask us for if we want the plot, and we'll see the plot. We don't get the ci table. If we use that ci table argument set to false, and we can do the same with the ci.plot argument if we like. We can set that to false to suppress the plot. And then we just get the cursor back. It's not asking us if we want to plot because we've suppressed it. Another option you have that's kind of unique to this function is the ci.level argument. You might recall by default the function outputted a 95% confidence interval. We can change that from the ci level. The default is 95. If we want a lower value or a greater value, we can increase or lower the ci level. Like for example, if I want a 90% confidence interval instead of a 95% confidence interval, I can change that ci.level argument to 90. And the last table, yeah, it gives me the 90% confidence interval of the difference in proportion. This should be a slightly narrow interval, and I've set ci.plot to false, so it's not plotting that. Now, one I think very useful argument. I'm gonna skip down to run this testpropsC, the fed-spend border against fed-spend crime to demonstrate the use of the response variable. I think that's the response argument. I think that's another one that's fairly useful. Now, you may recall when I ran this, it compared the proportion who think that spending should be increased a lot on the Border Patrol against the proportion that think that spending should be increased a lot on crime control. The response variable gives you a chance to change the response category that you're comparing. To get an idea of what I can do, I'm going to do a quick frequency distribution table of one of the fed spend variables. I'll use the border to look at the response categories. So you can see that the response categories are increased a lot, a little, kept the same, decreased a little, or decreased a lot. So depending on the type of analysis you're doing, you might want to change it if you're interested in, not whether people want to increase spending in these categories, but rather decrease spending in these categories. You could change the response category from the default, which the default is the first one. You could change it to any of the others. So I might say I want to compare the response who say that spending in these categories should be decreased a lot. So I would add on to the function call response argument and set the response argument to the value I want to compare. So like decreased a lot. You notice I copy and pasted that from the results of the freqC function just to avoid typos, and hopefully that will work. Let's give it a run. I think that's looking pretty good. So we're comparing excuse me, the proportion who think that spending on Border Patrol should be decreased a lot to the proportion who think that spending on crime control should be decreased a lot. The null hypothesis is the two values are equal. The alternative hypothesis is that they are not equal. We've got our descriptive statistics. 0.129 of respondents say we should decrease spending on Border Patrol a lot, whereas This is scientific notation. So 0.053 say that spending on crime control should be decreased a lot. We've got our z-test with our z statistic and a p-value almost 0, certainly less than 0.05, and we've got a 95% confidence interval. We see the point estimate of the difference, the lower bound and upper bound, and a plot of that. And you can see that the confidence interval does not contain 0, and we can see the plot to the point is above 0, and the boundaries, which are really kind of too small to be seen here, do not cross over 0. So we would confidently conclude that the portion of respondents who think that Border Patrol spending should be decreased a lot is different than the proportion of respondents who think that spending on crime control should be decreased a lot. And what I've done with the response argument is I just switched it from the increased a lot category to the decreased a lot category. So plot-related arguments. I've sort of already showed you one plot-related argument with the ci.plot argument that is by default true, but it can be set equal to false if you want to suppress the confidence interval plot. To make a plot, you can either delete that or you can explicitly set it to true if you like. Now, when I ran that, the confidence interval plot isn't quite satisfactory because in this case, because of the large number of respondents, the confidence interval is pretty tight, but because it's by default plotting between values of -1 all the way to +1, it's kind of hard to see that. And so like by default, it's really hard to know ahead of time the plotting, the plotting interval without knowing what proportions are being tested. So by default, the difference could be as low as great as -1 or as +1. So it kind of by default the plot spans the whole set of values. But in any given case, you might want to focus in on that more, and that's why we have this xlim argument. And the xlim is used to set the upper and lower bounds of the x-axis. So you can see if you look at the confidence interval table, the point estimate is -0.1. It's a little bit lower, a little bit higher than that. So you can use the xlim argument set to a vector and specify like the lower bound and the upper bound to focus in on the area that contains the interval to just be able to see it more clearly. Like, so for example, I could set the x limits to, on the low end, -0.2 and on the upper end 0. Let's give this a run and take a look at it. It should give us a more interesting plot. Okay, so this is better. So you can see start to see the dashed line that represents the confidence interval. Okay, so now we've got the point that represents the observed difference of proportions, and the dashed line is the confidence interval. So now that we've zoomed in on it, you can see the dashed line and its relationship to 0, and you can see that that there is a area of plausible uncertainty here, but that area, the confidence interval, is entirely less than 0. So we observe a difference between the two proportions, and just based on the hypothesis testing, the confidence interval, and the graphic display of the confidence interval, that it's not plausible to think that the difference is actually 0, because 0 is outside of the confidence interval. And it was a little hard to see at first, but if you zoom in using the xlim arguments, you can zoom in on the difference and see it better. And I would recommend, when you're doing this, try to include 0 or the hypothesized difference in the plot, because usually when you're doing this kind of hypothesis test, you're examining the difference relative to 0, so you want to see where the 0 is, but the other boundary can be reduced. And like in this case, like we certainly don't need to see all the way from -1 to +1. We really want to see a tighter interval like this for the plot to be more informative.